नंबर से आप संपर्क करना चाहते हैं वह अभी स्विच ऑफ है।
Good afternoon. Good afternoon.
Good afternoon, sir. Good afternoon. I was trying to call you on Zoom. So we can start now, sir.
Yeah, you can start. Let me see. How to share my file.
Okay. Yes, we are able to see that.
Okay.
One thing you can put in that presentation mode.
Yeah, it is in the presentation mode only.
Till now, I am able to see the page mode.
It's in presentation mode.
Okay. So you can start now, sir?
I think so. We can start.
Okay, sir. So I will take just 2-3 minutes and then I will hand over to you. Respected Dr. Madhavan Rajeevan ji, dear colleagues, scientists, administrative and project staff, students, ladies and gentlemen, wish you all a very happy 79th Foundation Day of CSIR. It gives me immense pleasure to welcome our Research Council Chairman, Dr. M. Rajeevan, Secretary, Ministry of Earth Science, to deliver the public lecture on CSIR Foundation Day. I'm very much thankful to him for sparing his valuable time for this lecture. It will be great to listen him on CSIR Foundation Day. As being the chairman of our RC, he is the scientific guardian of our institute. Dr. Rajeevan needs no introduction to this gathering. However, it will be appropriate to present his brief introduction for the sake of some of our younger and new colleagues. Dr. Madhavan Nair Rajeevan was born on 27 July 1961 and completed his master's and PhD in physics. He held many important positions. Dr. Rajeevan started his scientific career at Tata Institute of Fundamental Research in Infrared Astronomy Group during December 1983 to August 1985. And then he shifted as meteorologist, director of the National Climate Center at Meteorological Center Ahmedabad and National Climate Center India Meteorological Department Pune during September 1985 to June 2008. He worked as senior scientist F at National Atmospheric Research Laboratory, Department of Space, Tirupati during July 2008 to January 2012. Then he moved to Ministry of Earth Science as Scientist G Advisor of Government of India, New Delhi, at February 2012 to March 2015. And then he became the director of the Indian Institute of Tropical Meteorology, Pune, and he was working there during March 15 to December 15, or a very short while. And then he took this coveted position of Secretary at Ministry of Earth Sciences during 7th December 2015 till now. He is very versatile scientist and his research specializations are monsoon variability and monsoon prediction, climate change and extreme weather events, prediction of mesoscale convective system, cloud radiation interaction and satellite applications, and aerosol radiative forcing. For his contribution to this field, he has received many awards and honors, and some of them are 2001 Start Young Scientist Award for the paper Net Cloud Radiative Forcing at the Top of Atmosphere in the Asian Monsoon Region, published in Journal of Climate 2000. Award for Young Scientist in Atmospheric Science by Ministry of Earth Science, New Delhi in 2007 for research contribution in atmospheric sciences. 20th Biennial MOSM Award 2001, Department of Science and Technology for the paper Aerosol Cloud Climate Effect, a study with a radiative transfer model, published in MOSM. He is the fellow of all three academies, Indian Academy of Sciences, Indian National Science Academy, National Science Academy of India. He is a member of International Academy of Astronautics. High-level advisor on climate services, World Meteorological Organization. He is the expert member of Research Board of World Meteorological Organization. He is the chairman, Board of Governors, Indian Institute of Science Education and Research, CSIR Thiruvananthapuram. And he is also the chairman of Council of Regional Integrated Multi-Hazard Early Warning System for Africa and Asia, Bangkok. Actually, he had, I think, so many, it will take a lot of time. So without taking much time, I'll move further. And his scientific contribution, if you see, he has published more than 120 peer-reviewed publications with total citation of almost about 8,000, and each index is about 45. So it says about his scientific credentials. So I'm really very happy to have him to deliver this talk. Once again, I welcome Dr. Rajeevan, and I request him to deliver the public lecture entitled Observed and Projected Climate Change over the Indian Region. Thank you very much.
Yeah. Thank you, Dr. Sunil Singh, for first of all for inviting me to give a talk on this CSIR Foundation Day, and I would like to wish all of you happy CSIR Foundation Day and wish you all the best. CSIR is a huge scientific organization. In this difficult COVID time, CSIR is doing extremely well, leading a lot of initiatives related to COVID, in terms of vaccine, in terms of tools for testing, etc. And NIO also is playing its own role for doing the work related to COVID. NIO, as all of you know that very well, so you are a part of the NIO system, and I am also last 3 years I have been working as the chairman for RAC Research Council at NIO. NIO is a premier research institute and more than 50 years old now. I've been doing a lot of good work, excellent work in oceanography. And as all of you know that in India, ocean science is done by very few people, very few institutions are there in India who's doing a good research in ocean. So we need more and more good people to join in oceanography and doing a lot of work for the country. Today I have decided to talk little different from oceans and related to climate change because I thought it is I understand it's a popular lecture. So I thought all people will understand anything if you talk about our own climate and climate change. So I'll be talking about, take about half an hour to 40 minutes maximum about what we have observed so far and what is our future climate change, especially over the Indian region. I hope that I am audible to all of you, and also I hope that all of you can see my presentation very well.
Yes, sir, it is very much clear.
Okay. So if you really talk about Earth climate system, it consists of 5 spheres: and atmosphere, hydrosphere, lithosphere, cryosphere, and biosphere. And these 5 spheres are not independent; they are all interactive systems, especially nonlinear interaction. For example, atmosphere can interact with the hydrosphere, cryosphere can interact with atmosphere, atmosphere will interact with the hydrosphere, especially with the ocean. So it's a mutually interactive system, and life exists everywhere near the Earth because the climate is very favorable. And natural variation of the climate system arises from interactive feedbacks from these climate system components on different time scales. So if you really talk about Earth system or its climate system, these are the essential components. And if you really talk about Earth system, we should understand what are these systems. So for example, sun solar radiation is the primary source for driving the Earth's climate system. Without sun, we do not have a climate. And so sun solar radiation is in basic inputs. It passes through the atmosphere, so it interacts with the aerosol, it interacts with the clouds. It reaches at the surface. It heats up the surface. About half of solar energy reaches at the surface. Then it is converted into fluxes like sensible heat flux, latent heat flux, etc. In the atmosphere also there are many other processes which happen. For some cloud formation happens, moisture surface it goes up and it condenses into clouds, and different kinds of clouds formation is happening. And some clouds will give rain, some clouds will give very heavy rain, some clouds very little rain, but clouds are formed every time. And then also we have biosphere, we have also cryosphere, which also interacts with the climate system. So it's a highly nonlinear and complex system. If we really want to know what is our climate and how it is going to change, we should know how these activities are really happening. So that is our basic difficulty. So our basic understanding about the nonlinear interaction of these systems is now better, but still we don't know many things. We don't know many things, which of course I will talk in detail. What are the causes for climate change? There are mainly two causes. One is it can happen between any reasons due to internal cause. It can be within the system or due to external cause. External cause is anything outside the Earth system. Say, for example, change in the intensity of solar radiation can change the climate, or change in the orbital parameters of the Earth can change the climate, and also the rate of rotation of the Earth can change also the climate. But this won't happen in a short time span. It happens in years together, 10,000, 20,000 years together. Probably small changes can happen, especially in solar radiation, and also orbital parameters and rate of rotation, etc. But what we are worried now is of internal causes due to increase in especially fossil fuels, so-called greenhouse gases. That is mainly caused by anthropogenic activities, human activities. And internal cause, another example I can give, which can change the climate, at least on a short lifespan, is a volcanic eruption. But it's a natural cause. It is a natural process where nobody forces a volcanic eruption. So the climate can change both mainly because of the internal causes, and within the internal system, fossil fuel burning is the most important. And if you really calculate the presence of or estimate the concentration of two main greenhouse gases like carbon dioxide and methane, you can see this is the kind of structure we get. And you can see the last few years from 1900 or so, there's a rapid rise in carbon dioxide as well as methane, and correspondingly temperature also has gone up, and especially last 40-50 years. So the change, the increase in carbon dioxide and methane during the recent period is very unprecedented. It will never happen in the recent past, at least some 400 kilo years before 1850. And carbon dioxide, as far as carbon dioxide is concerned, the first observational data has come somewhere in mid-50s, late 50s, 1950s. He's the person, Charles Keeling, is a very famous person. He is the person who set up this observatory in Mauna Loa, carbon dioxide observatory. And still it is going on very well. And what we know about carbon dioxide, what we know about climate change, and all mainly because of his he's alone, one-man army kind of person who does very meticulous observations over this observatory Mauna Loa and collects these observations and pass on to many people. And this is the kind of observation. Right-hand side top, you can see the red color. This is the level of carbon dioxide increase which we have seen in this Mauna Loa observatory. It was some less than 320 parts per million about 1960s, starting of 1960s. Now it is crossed 400 and 420 or so now. So almost 100 ppm increase of carbon dioxide happened in last few years, last 60 years or so. So it's an unprecedented change in the carbon dioxide and other greenhouse gases like methane and also nitrous oxide, etc.
Sir, slide is not changing.
My God, slides are not changing. I am changing here.
Yeah, I got some message from other people also that it is not moving.
So what I should do? Now it is changing.
Not yet. Yes.
Sir, I think slideshow mode, it is not there. What we are seeing is only the presentation slides which are not in the slideshow mode. So if you put it in slideshow mode, it will change at both the places.
So I am doing it in slideshow mode only.
In this case, you may have to share the whole screen rather than just sharing the presentation, sir.
Oh, okay. So you tell me how to do it.
Now it is changing, sir. Now it is changing.
So I will try once more and now you are able to see the slide.
We are able to see climate change slide.
Okay, that's the same thing. Now it is changed.
Not yet. I still climate change.
I'm changing here. I'm not sure. Maybe the problem with the internet.
Now it has come to CO2 problem. Oh, sorry.
Sir, sorry to interrupt. Please put in a full screen mode.
Which one? The screen?
Yes.
Full screen.
Full screen mode.
Okay.
Right now,
presentation is now presentation is on slideshow.
No.
Carbon dioxide problem.
No,
Please,
sir.
now it is not sharing.
Okay.
Click on screen sharing. Take a full desktop window.
Oh, can you see? Can you see now?
Yes, yes.
Okay, now I will go on to slide mode.
Yes.
Slide mode now.
Yes.
Can you see now?
It's not it.
Still in not in slide mode, but we are able to see in in PPT mode only.
I don't know. Maybe a problem.
So right now we are seeing CO2 problem.
Yeah, so CO2 problem. So can I go proceed? Can you see me?
Yeah, means you can continue with this.
Yeah, let me try. Can you see now? Next one.
Not yet, sir.
It is. I'm sorry. It's a very slow process now.
Otherwise, sir, you don't put in the slideshow mode and just change the slides here only.
Now it
because
came.
we are able to see this.
Pardon?
Now, next slide came, land use changes.
That's true. I think it is little slow. That's what I feel.
Yes, sir, yes.
Can I go slowly then?
Yes, sir, please go ahead.
Yeah, okay. So this, so in addition to this greenhouse gas changes, land use changes also happening because of our human activities, especially we are removing forest and making into agricultural land, and we are removing forest and making some other buildings, etc. So land use changes are happening rapidly everywhere. So this also can cause to climate change. And why these changes can happen, why these changes should lead to change in climate. If you really see the Earth's energy balance, and as I said that sun solar radiation is the main source for sun's energy, our energy. And once we receive energy, our the main physics, laws physics says that any body more than 0 degree Kelvin should also emit IR radiation, thermal radiation back. And so Earth's temperature, it has a temperature, so it should emit some radiation back, and we call it IR radiation or thermal radiation. So what is the radiation received from the sun will be equal to what is the radiation going out from the Earth's system. So then the climate will be balanced, and there will be a balance in the energy, and the climate will be in equilibrium. And if any change in the thermal, any radiation, either incoming solar radiation or outgoing thermal radiation, if any imbalance happens, that will lead to imbalance in the energy balance, and that can lead to climate change. And so what is happening now is we are receiving solar radiation from the top of the atmosphere, but because of these greenhouse gases, there is an effect called greenhouse effect. And the thermal radiation going from the Earth's space is limited, and it's reflected back to Earth's space. And some thermal radiation is not allowed to go out. So there is that is retained within the Earth's system. And so there is a energy imbalance, and that can cause really the climate change. So Earth receives more radiation than otherwise we are supposed to expect. So mainly because greenhouse gas is increasing, and greenhouse gas can allow the solar radiation to come in, but don't allow the thermal radiation to go out. So that is the problem. So that will create an imbalance in energy balance, and definitely will lead to the imbalance in the energy balance, and it can cause the climate change. And this is the greenhouse effect is well known. I will skip on that. I will. This is the, for example, 1380 watts per meter square is the energy received from sun, and same kind of radiation it goes back to the space. So now I will come to the observed changes in the climate system. So far, we have observations from last 150, 170, for example, 1850s and all. We started observations. Temperature, rainfall, humidity, etc. So we really analyze those observations, what we have seen. So that I will describe in next few slides. First, I will describe about the global picture, a few slides. Then I will specifically say what has happened in India's climate. And of course, we have a subject called paleoclimate, and I know some of you in NIO also does a lot of work in paleoclimate using the proxies from ocean and especially sediments, and they do try to find out what is the past climate. And if you really see the surface observations of surface air temperature last 150 years or so, what we have found that there is and if you really analyze last 1850 onwards, 170 years of data, and analyze the temperature trends all over the globe, and this is the temperature change what we can observe is that there's warming everywhere throughout the globe. All the parts of the globe is warming up, and warming is of the order of 1 degree, some places 2.5 degree or so the last 150 years, 170 years. So warming is very large, and also warming is not uniformly distributed. Warming is more in some places, warming is less in some places. Especially warming is more in Arctic region as well as in the Antarctic region. Arctic region is more warming than any other place. And then this phenomena we call Arctic amplification. And mainly because it has an internal process, internal feedback process is happening in the Arctic climate. And mainly because of that, the Arctic temperature is going up much faster than any other place. So Arctic warming is much more than any other warming. So warming is not uniform. And Arctic amplification has its own replication, its own implication, which I will speak little later. And if you really calculate the time series, you take all the temperature observation from the whole globe and plot it in terms of anomalies, and this is the picture which we get. And you can see that first few years up to 1950s, temperatures are very cold. Then, especially from late 70s, mid 70s to late 70s, temperature started picking up. And you can see this unprecedented warming is happening everywhere throughout the globe. So even global average is very large, and temperature has gone up almost more than 1 degree, 1.2 degree temperature warming has happened. The same temperature, and we have different research groups form different data sets, and if you analyze all the data sets say the same story, that temperature has warmed up, especially after 1970, mid 70s, 1975 or so. The temperature increase has become very large. And if you really bifurcate that temperature data between land region as well as oceanic region, the land region is warming up much faster than the oceanic region. Ocean region takes little more time to warm up, whereas land region is very quick in responding to global warming. And so the temperature over land region is much more, the warming is much more than the oceanic region. There's a big difference between the warming in the land region as well as the oceanic region. And if you really plot the annual cycle of temperature anomalies starting from 1880s, these are all blue in color. And 2019, last year, how it was, it is in red in color. You can see that it's an appreciable change in the temperature, not only in one particular month, but throughout the month. Throughout all 12 months, temperature has been warming up everywhere. And these are global anomalies, and you can see that throughout the globe, all the months are warming up. It's not only one particular month is warming up. So the warming has a lot of replications. So global warming is very much confirmed. Last 150 years, it has warmed up almost 1 degree or so. This warming is very unprecedented, and it can have a lot of replications. And I will briefly tell what are the replications and whether we have really started seeing this effect of global warming in some parts of India. And for example, sea level rise, of course, you are all oceanographers, you know very well how sea level rise also is happened, mainly because of temperature change, because it's thermal expansion. Of course, there are many other reasons for sea level rise. Thermal expansion is one of them. And also very interesting to see that sea level rise also is not very uniformly distributed. At different places, the warming, the sea level rise, the trends are different at different places. And if you really see the time series, you can see it's also the last 30 years, sorry, 1993, when we started having the satellite observations. We have the satellite observation from early 1990s, and up to even 2020, we have the satellite observation, which shows about 50 millimeter or so rise in the sea level, global sea level rise. This is the sea level rise. It is announced by WMO, World Meteorological Organization, starting from 1993. These are all satellite data, and you can see that almost 80 millimeter rise in the sea level. Global. This is a global average, 75 millimeter or so. So global average. And so not only the sea surface temperature has changed, and even the ocean heat content, and which is also a very important parameter in terms of global warming. So the temperature is not warmed only at the ocean surface, sea surface, but it has also penetrated to a depth up to 100, 200, 300 meter. And if you really calculate the ocean heat content, and that also is increasing. Ocean heat content data, people are Argo flows, from Argo flows we can calculate. Otherwise, also see this from the satellite data from the altimeter you can calculate and you can convert back into ocean heat content. And this ocean heat content, if you really plot a time series from 1955, also shows a very large increase in the ocean heat content. Ocean heat content has a lot of implication in terms of, for example, tropical cyclone. Tropical cyclones, tropical cyclones are oceanic phenomena, and the ocean temperature is very important for tropical cyclone for formation as well as its movement. Also, it's for intensification. But now recent studies very clearly suggest that not only the ocean sea surface temperature, but it is also the ocean heat content is playing an important role in especially in intensification of tropical cyclones. So that is more important. And it has a lot of repercussions in intensification of tropical cyclones. So now recent studies throughout the globe, in many places, many oceanic region, many ocean basins, the tropical cyclones data, if you take and analyze it, we find that the rate of intensification, that means how much wind speed has increased in 12 hours, how much average, how much wind speed increased in 24 hours. If you really calculate for each cyclone and put an average for a particular year, then make a time series, it clearly shows the rate of intensification is rapidly increasing. And so the cyclone once forms, it intensifies into a very severe cyclone, into the next higher level, very fast, very quickly it intensifies. It takes very less time for intensification. And that could be related to, of course, many factors, including vertical wind shear in the atmosphere, and circulation features. But ocean also plays important role. Many papers are coming out saying that the tropical cyclone intensification, quick intensification, is also caused due to the ocean heat content increase. And I will give you one good example. This is a paper came in Advances in Meteorology, which they analyzed the Northwest Pacific cyclones, where the cyclone number is much more than any other oceanic region. And here it very clearly shows that, I don't know whether you are able to see it properly. I'm very sorry about it. And the green line, which shows the SST in the left-hand side, or right-hand side is the ocean heat content. It clearly shows that a few hours, 24 hours before the rapid intensification, the ocean heat content and SST are much larger than any other cyclone, which are not really intensifying. So the meaning is that for intensifying a tropical cyclone, ocean heat content plays an important role. Then, of course, this is also an important agenda. I am very sure that NIO, some of you are working on the ocean acidification, because as all of you know that carbon dioxide, what we are emitting is some of the carbon dioxide, almost 50% is absorbed by ocean. And oceans, our pH value is changing. Ocean is becoming more acid now. And this process is known as ocean acidification. I'm very sure that some of you are taking observation of how much ocean acidification is happening. And NIO should really lead a research effort to understand how ocean acidification is really happening, especially in the Indian Ocean. The next slide shows how Arctic, I told the Arctic amplification is happening. And Arctic amplification is mainly because the internal process in the Arctic region and Arctic climate system. And the Arctic region is warming much faster than, much more than any other region. And that is really causing Arctic sea ice melting. And if the Arctic sea ice melting also, especially not the depth, but also the aerial extent, sea ice extent, can be calculated using satellite. US satellites, especially the defense satellite like SSMI data, clearly shows, these are microwave based data, and which clearly shows that sea ice extent can be calculated. So if you really have long time series from 1980s up to 2017, 18, 19, the analysis of satellite data very clearly shows that Arctic sea ice is melting much faster, and especially from 1995, the decline in the sea ice extent is much faster than in many other places. So Arctic sea ice melting is very certain. And if somebody asks you what is the how can global warming can affect, can you give me an example how global warming can affect any particular system, climate system? You can easily say that Arctic sea ice melting is one of the best example of the effect of global warming. So global warming, the Arctic sea ice melting in Arctic sea ice, Arctic region is mainly caused by the increase in the temperatures. Of course, there could be a lot of natural process also happening over the region, which we are not understood properly. But if we really analyze all the effects, global warming plays an important. And if you really see the climate change model simulations by climate models, very clearly shows that with using climate models, we can calculate how CS is going to change in the future. And if it very clearly shows that by 2050, another 30 years, in the September, October, November, so that period, that is the period. September is the month in which we get the lowest CS section because melting will be picking up in the month of September. And in the month of September, we will have a Arctic sea without any ice. So we will not have any ice in September. The September will have Arctic sea will be without any ice. It will be simply ocean. So that is the projection. It's very, very alarming. Of course, people are talking about the economic benefits of an Arctic Ocean without sea ice because ship can go to any place and people can take out oil from there. People can take out minerals from there. So people are talking about the resources coming out from Arctic, economic benefits of Arctic sea ice melting. But the climate people are saying that changing the climate Arctic sea ice is not really good because it has a lot of repercussions. It has an effect. It has an effect in not only the weather system forming over Arctic region. It also has an effect in weather system occurring over middle latitude region, especially in Europe. I will give an example. Even in Indian monsoon region, Arctic sea ice melting has an repercussion, has an effect. We in meteorology we call teleconnections, and that means two regions are connected through a physical mechanism through atmospheric process, and anything causing in one region can have an effect in another region. So Arctic sea ice melting can have a very serious repercussion in Indian monsoon region. So that is the good science coming out. A lot of research is going on, and if somebody is interested in doing what will be the effect of Arctic sea ice melting in Indian monsoon region, this could be a good research problem. And our sister organization NCPOR, which is also in Goa, is doing a lot of work in Arctic. They have a station in Arctic, and they are doing a lot of good work. The 2008 onwards, they are taking observations over that region. And what will be the change in the effect of climate change is statistically, if somebody is good in statistics, they will know. And if a mean is changed, assume that it is a normal distribution, Gaussian distribution. Any change in the mean can cause in the change in the extremes. And not only in the mean, even if the variability changes also can cause the extremes. And both mean and the change in the variability also can cause the extreme. So the effect of climate change, the mean temperature change, and what we are talking 1 degree change, really means the extremes also can change. And there are a lot of good examples that in climate, the extremes are changing everywhere. Over the Indian region, I will give a good few examples of how temperatures and everything has changed over the Indian region. This is the surface air temperature trends over Indian region of different seasons. If you can see that chart, it clearly shows that this is a T minimum, T maximum, and T mean. And that's mean maximum temperature, minimum temperature, and mean temperature at different seasons, annual, December, January, February, March, April, May, JJS, and October, November. It clearly shows that warming is there everywhere, and the minimum temperature has warmed up much more than the maximum temperature. So warming is there everywhere throughout the India, many parts as warming is seen. And if you really plot the temperature curve for all India temperature curve, it also clearly shows the temperature increase in starting from 1980s. And if you take last 70 years or so, last from 1980s, last 50 years of data, the temperatures changed almost 0.6 degree or so. So warming is also happening not only over the whole globe, but it's also happening over Indian region. And by Indian region also, warming is uniformly distributed throughout the place. And Indian Ocean SST, which of course you people may be knowing better, for Indian Ocean warming, as all of you know that among all the ocean basins, Indian Ocean is warming much rapidly than any other ocean basin. There could be a lot of reasons for that. And it has a lot of implications in terms of extreme weather events over Indian region, etc. And so this also very clearly shows that very large warming is happening over the Indian Ocean. And if you talk about past climate, monsoon precipitation, we have data, proxy data, paleoclimate data for the last 4,000 years. And the monsoon rainfall is the most important characteristics of monsoon rainfall is it has large multi-decadal variations, not only year-to-year variation, but multi-decadal variation. Some decades monsoon will be very good, then followed by another few years, another 30, 40 years in which monsoon will be very bad. So this multi-decadal variation is not only seen in the observations in the recent years, but also seen in the even in the paleoclimate with the proxy data. Proxy data in terms of speleothem or any other data, if you take and analyze it, you will get the same kind of results. And if you take the last 150 years of monsoon rainfall and analyze it, you will see that there's a good news that if you take all India average of monsoon rainfall, monsoon is very stable, monsoon is very robust, and there's not big changes in the all India monsoon rainfall. Still we get well enough good monsoon rainfall. This year, as all of you know, it's really raining everywhere. But if you take region-wise analysis, there are some regions where you get less rainfall, decreasing trend, and there are some regions where the rainfall is increasing trend. So the rainfall trends are not uniformly distributed. But if you take an all-India average, you will get a robust monsoon. That means monsoon is not really changing. And then also heavy rainfall, if you really take any monsoon season and see the rainfall events actually exceeding 10 centimeter in a day or 15 centimeter in a day, the rainfall, heavy rainfall events also increasing everywhere. This is the frequency distribution. And if you really plot the time series, you can easily see that the rainfall events are increasing everywhere. Heavy rainfall, especially over northern parts of the country. And rainstorms is an example. You must be aware about the big flood events happen, which is in Jammu Kashmir, Srinagar, for example, recent years, and also the famous Uttarakhand rains, heavy rains and floods. So they're all caused by large-scale heavy rainfall events. Not only in a small few hours, it happened in 2 days, 3 days in time. We call these are all rainstorms. And rainstorms frequency also is increasing, not only rainstorm days, events, but also rainstorm days. The days in which rainstorm is present is also increasing. So we are getting monsoon, even though monsoon rainfall may be uniformly distributed and also there's not much trend. But within the monsoon season, when rainfall occurs, it occurs in very heavy spells. So that's very important. When it rains very heavily everywhere, most of the places now. So that is really has a lot of implication because it can lead to flash floods. It can really cause damages in the agriculture, etc. And another one is a heat wave. You must be heard about the European heat wave in 2003, in which about 40,000 people died in countries like Central Europe, countries like France and Germany and some places of Belgium, etc. 40,000 people died, and it's very unprecedented. And 2000 European heat wave is well known, and many research papers have come up why that heat wave really occurred. So such kind of heat waves are happening over Indian region also. This is a time series over Indian region. You can see that warm days are increasing, and also warm nights are increasing. Whereas because of the global warming, we are not getting cold nights. The cold nights frequency is coming down, and even in Delhi, I'm here for last 5 years. Except for last year, otherwise the winter is not that severe now. And last year, of course, the winter was very, very bad. And but not only in Delhi, many places in India, northern parts of India, cold nights are decreasing. The nights are not that very cold, but days are becoming very, very warm. So warm days are more, but cold nights are decreasing, mainly because I told that warming is happening everywhere. And this is the frequency of heat waves at the different places, and there also heat waves is increasing. Another aspect in the dimension in the temperature, sorry, climate change is the aerosols. Aerosols, all of you know that aerosol also is caused by mainly by, of course, there are two ways of doing. One is a natural process, natural aerosols. For example, dust from desert is a natural aerosol. But sulfate aerosol, for example, it is a kind of aerosol is caused by human activities. And carbon dioxide is when fossil fuel is burned, it's a carbon dioxide is emitted. Also, sulfur dioxide is emitted, and sulfur dioxide can cause to sulfate aerosol through a chemical process. And sulfate aerosols also form. Sulfate aerosols really have a cooling effect. It normally scatters solar radiation. And then also there are aerosols called black aerosols, black carbon aerosols. And that has a different effect than sulfate aerosols. Sulfate aerosols normally has a cooling effect, but black carbon aerosols normally has a warming effect because it absorbs the solar radiation, whereas sulfate aerosol scatters the solar radiation. And and this black carbon aerosol is also an important concern over the Indian region, how it can affect Indian climate change. So that also is a area of serious research. Now, next a few slides, another 10-15 slides, I will finish it up. I will show that how the future climate will be. And if you really want to know the future climate, what we need is we need an Earth system model. What is Earth system model means? I shown in the beginning a figure in which all the Earth system components were shown, and different components like atmosphere, ocean, as well as rivers, cryosphere, and cloud process and land surface processes, etc. So all these processes should be modeled. It should be done in a physical way, and then some mathematical equations are solved, and to find out what will happen in the future climate. So that's what we call a system model. So a system model is similar to our weather prediction model, but much more advanced in terms of physics. And also, of course, the resolution will be much poorer when compared to weather prediction model, but it will have more physical process. Like, for example, biogeochemistry will be an important component. Biogeochemistry may not be very important for weather prediction for next 3 days or 4 days, but biogeochemistry is very important for climate, in the climate time scale, maybe 40 years, 50 years time scale, biogeochemistry plays an important role. Similarly, deep ocean will not be important, will not have important role in short range weather forecast for next 4 days or 5 days, but deep ocean will play important role in climate. So the components of physics will be different, but the basic structure will be same, solving some few mathematical equations and also carrying out the physical processes. And these are the equations. We have 5 equations. We can solve these equations. And these are all nonlinear differential equations. So we don't have analytical solution. We need to really solve using some mathematical methods, finite difference or spectral harmonics methods we have to follow and solve these equations. We'll skip this and once we once we know this, once we have a climate system model, we can do a projection for climate. So I use the word projection. That's very important. So anything, if you talk about next 30 years, 40 years, we cannot say it's a prediction. Prediction we can talk about 1 year, 2 year, but not on a larger time scale. So it's all, we call this a projection. So it has a lot of uncertainties. So that's why we call this a projection. So we should never say climate change prediction. Climate change projections are more important than the climate. So we don't do prediction. We really make a projection and using climate model. Sorry, a system model. So recently in our institute, IITM, Indian Institute of Tropical Meteorology in Pune, we have a center called Center for Climate Change Research, and that center has recently developed a system model. This is the first time in India we have developed our own system model. It's a very huge teamwork, and it's very fabulous work which they have done. And using this model now, IITM is preparing what will be happening in the future climate, and many other groups are preparing throughout the world. and India also is participating in the IPCC climate change assessment report, which is going to come in 2022. And S system model, our IITM S system model will be a part of the climate change assessment report. For doing this climate change assessment as well as for doing the S system modeling, we need huge computing power. So thanks to the Indian government, we have updated our computer resources for about 3 years back. We have a beautiful computer in Pune. It's called Pratyush, and it has capacity about 7 petaflop or so. And we have another center in Noida. We have another computer there. Put together, we have about 10 petaflop. A 10 petaflop computing resources is the fourth best in the world among the weather prediction centers around the world. After the US, UK, and Japan, we have the best computing facility in terms of which is used for weather and climate predictions. And so this Pratyush is extensively used for making climate change projections. And I want to make an advertisement for this book. I'm not sure whether you are still able to see my slides. Otherwise, I'm very sorry. I will share my presentation, and you people can download it and see it comfortably. And,
no, sir, we are to see your slides.
Okay, very good, very good, very good. And this is the advertisement I want to make. This is assessment of climate change over the Indian region. MOES has first time brought out a national climate change assessment report. Many of you may be knowing about IPCC climate change report, which comes in every 4 years or 5 years. 5 reports have come up. The 6th report will come in 2022. And in the IPCC report, the problem is it's a global report. They don't talk about anything very specifically about some regions. For example, Indian region, what will happen, what will temperature, humidity, they will very few discussions will be there. So if you really want to know what is really happening over the Indian region, we need to have a separate comprehensive analysis over the Indian region. So this was done by our group people, our good people in Climate Change Center in Pune. Dr. R. Krishnan and group has come out. Last 2 years, they have been working on this report. It has come out. The report was released a few days back, and this report is available free of cost. It's online. It's available. Anybody can download it. So just go to Google. It is published by Springer. Assessment of Climate Change over the Indian region. You will get the link. You can download it free of cost. Please go through the book and read comfortably. It's a beautiful book, a beautiful climate change assessment report which they have made. So I will show a few slides from this report, which I thought it will be interesting for you. So we should know what is going to happen. But before I start discussing about what is going to happen, I should really caution you that the climate change projections, as again I said, that it's not prediction, it's a projection, also has a lot of uncertainties. And these uncertainties, you should keep it in mind. Whatever climate change projections are being told to you is not the final word or Bible. And there could be a lot of uncertainties. And but it gives you an idea, it gives you an indication what we can expect in next 30 years or 40 years or 50 years. There could be changes in terms of quantitative changes in terms of prediction, so in terms of projections, but qualitatively the sense will be the same. So what is going to happen in the next few years is especially in temperature. So in climate change projection, they make scenarios. We call scenarios. We don't know how in future fossil fuel will be burned, how much fossil fuel will be used. Depending upon the scenarios, the climate change scenario will be also different. So what we do is normally we assume some kind of a scenario of how all the countries will be using carbon dioxide or in general fossil fuel. And one is business as usual. Assume that we will not make any changes in our policy. We will burn as we are doing now. We will not go, for example, non-conventional energy sources like wind or solar energy. We will simply burn coal and petrol, and that is a business as usual. And if so, what will happen in our future climate? Second is we can put restriction, and like India is doing now, we are trying to go for wind and solar energy so that our fossil fuel consumption will be reduced. Then what will happen in such scenario? What will happen to the climate? So these are two kinds of broad scenario we call, and we call RCP 4.5 and RCP 8.5. And RCP 8.5 is too serious, and it is beyond our comprehension. So we should not really consider RCP 8.5. RCP 4.5 is reasonably, we can expect that will happen. And if you really talk about RCP 4.5, by 2000, by 2040, 69, we can expect a temperature change of about 2 degrees. That is the time range. And if you really calculate the temperature change of longer period, it will be can be even 2.4 to 2.5 degrees. And but monsoon rainfall is a good news that monsoon rainfall is not going to decrease. It is going to change little bit, increase little bit, mainly because when temperature increases, you can expect more evaporation to take place. So you will have more moisture content, more moisture flux that can lead to increase in the monsoon rainfall. So we can expect next few years monsoon rainfall can increase. But as I told that the quantum of rainfall may increase, but along with that you can expect that the number of frequency of heavy rainfall also will increase. And similarly, in the Hindu Kush region, I will give 2 slides about how the Himalayas is changing. Himalayas is very important for all of us because it protects us in many ways. It is a heat source for monsoon. It's an environmentally very fragile system. So we need to know what is happening in our Himalayas region. Himalayan temperature also will go up, and 2040 time scale temperature change can be expected about again 2 degrees over Hindu Kush region, and there also snowfall can increase over that particular region. So these are all small good projections. These are all average projections which from our S system model which has come out from our analysis. And this is the spatial distribution. The top one is 4.5. You can see that temperature is going to change everywhere at the order of about 0.5 to 1 degree, 2 degree or so everywhere. The temperature is going to warm up. And this is the, if you really plot the all India rainfall, temperature time series, you can see that there are green lines, blue lines, and red lines. Red lines I told it is RCP 8.5, which is unreasonable. And blue line is reasonable. It's called RCP 4.5. So if you assume that RCP 4.5 is going to happen, by 2100, we can expect about 2.2 degree warming. It can happen. So that is the warming we should expect from the mean climate from today. If today's temperature is about average is about 16 degree, we can expect about 2 degree change in the 2 degree. We may feel that it is on daily, of course, day-to-day basis, 2 degrees nothing. Every day, today it will be 28, tomorrow it can be 30. But on a longer time scale, 2 degree has a lot of meaning, and it's really not good. And when you really calculate extreme temperatures, the top 2 panel very clearly shows the cold events will decrease. Already with observed data, we have seen that cold nights and cold days are decreasing, and it is going to continue. So we will have less and less colder nights will be there in winter. So winter will not be very harsh in Delhi and northern parts of the country. That's a good news, especially people like me. Staying in Delhi will be very difficult. So the next 30-40 years, I may not be there. But people who want to stay in Delhi, the winter will not be that severe. That's the projections which they made. But whereas in temperature during daytime will be very harsh. And many warm nights and warm days are going to happen in the future. So you can see that increase in that bottom 2 curves very clearly shows that temperature is going to warm days and warm nights are going to happen. The next is the heat wave days. The heat waves, as I told that it normally happens during April, May, June. Many heat wave events happen in India, and about 4,000, 5,000 people used to die in a few years back. But now the number has come down because we are able to predict them well in advance now, almost for 4 to 5 days and before. And because of that, the heat wave death due to heat waves are reduced. But the climate change projection very clearly shows that days in which heat waves are going to happen also is going to increase over the years. So that's also it's not a good news. And as far as precipitation is concerned, everything is in green color, so we should be happy. Left-hand side shows RCP 4.5 scenario, and right-hand side RCP 8.5. We should really discuss only RCP 4.5 scenario, which very clearly shows 3 models are shown. for different period, annual JJS and October, November, December period, very clearly shows there is going to be a small increase in the monsoon rainfall. So quantum of monsoon rainfall, water availability will be there. So there will be no reduction in total water availability in the country. So that's a big news. It's a really good news that we'll still have adequate amount of rainfall which we will be getting. Only thing is that the characteristics of monsoon rainfall is going to change. When it rains, it will be raining very heavily. So in that sense, then our water resources management practices should really change. We should preserve the rainfall. Once it falls down, we should not allow the water to go. So that's our, so rain harvesting is an important mantra to happen in next few years. When rain happens, you should preserve the water because we don't know when the next monsoon, when the next spell will come. It rains very heavily, but you store it in some places very carefully. And so that's kind of a change in our strategy, and water resources management should be very important. And also the extreme precipitation, you can see that the three curves very clearly shows that even though a small change in the mean rainfall, but extreme precipitation can give rise to a large increase. So we can expect large increase in the heavy rainfall events over too. So you can expect events like flash floods, like Bombay, when it rains 12 hours, 13 hours, we will have simply the whole city will be flooded. Such kind of events are going to happen more in the future. And this is the projected SST temperature. You can see that 2040 to 41 to 70 range is about over Indian Ocean is a 0.6 to 0.8 degrees warming is happening, and it's again warming is not very uniform. Arabian Sea is warming up much more than any other region, and especially Western Indian Ocean and Arabian Sea is warming much more. So it will have its own implication. Okay. And this is a time series of projected time series from 2040 to 2100. You can see about 0.35 degree warming can expect from every decade. If you really for RCP 8.5, RCP 8.5 is not very reasonable. 0.13 will be RCP 4.5. About 0.13 degree warming we can expect for every decade in the Indian Ocean. So last 3-4 slides I will show about Himalayas. As I told that Himalayas are very important region. It's very sensitive, and especially by biodiversity is very sensitive. But we have very few observations. That's very unfortunate situation. Is we have very few observations on Himalaya, mainly because we are not able to go there and put observations and maintain them. But satellite observations are very useful for understanding how Himalaya is changing and going to change. And with the available data, this Krishna's group has done this analysis how the Himalayas will change, in Kush region will change, and we have seen this observation from 1950 onwards. If you really plot Himalayan region, you can see that along with the Himalayan region has warmed up much more than Indian region, and the warming is much more in Himalayas. That's very important news. And last few years, the warming is much more in Himalayas, in the Kush region, and it has its own replication. And if you really see the future projections, if you really see, left-hand side shows how the things are going to change in annual, in a yearly time scale, and right-hand side shows how winter climate will be. Both shows the temperature will go up, and for different scenario, you can see the temperature with the x-axis is nothing but the years. You can see that surface temperature is going up, precipitation also is going up. But snowfall is going to decrease because warming will give rise to less snowfall, and melting also can happen, and especially ice melting can happen, snow melting can happen, and but a little change in the precipitation, and but large increase in the surface temperature over Himalayan region, which will have its own repercussion in terms of the dynamics of the Himalayan region ecosystem. So it can have effect in biodiversity, for example. So we don't know how this is going to have a non-linear effect in the ecosystem of biodiversity of Himalayan region. It's really a gray area where hundreds of students can really do research. How our Himalayas is going to change, how Himalayan ecosystem is going to change. we will have serious implication of changes occurring in the Himalayan region. So I think we should, may not be ocean NIO people, but definitely the research community in the country should really take it up a lot of work in doing work on Himalayas. And this is the precipitation change which we are expecting. For example, this is a threshold more than 90th percentile or so. A small increase in the precipitation is expected from this climate model. I am going to finish this presentation. So NCP, our organization, MOES organization in Goa, has set up an observatory in Himalayas now to understand how Himalayan glaciers are going to change. And it's not Himansh. I have one fine morning I went there using a helicopter. It's about 4,500 meters above. It's really a good experience for me. And I found that a lot of students who are sitting and doing research there, taking observations, etc. Of course, we do it only during a summer period. We cannot go in winter, and because winter will be completely covered by snow. So it's called Himansh. So they are taking a lot of observations of how the glaciers can melt. So probably we need such kind of more observatories in the Himalayan region for that, not only by MOES, even the organization like DST, CSIR should be able to put a lot of observations over the Himalayan region and study. So I will last 2-3 slides is what is sure for next 30-40 years. This is a summary of what I have told is increase in surface air temperature is very sure, and so temperature goes up, humidity level also will go up as an increase in heat waves is very sure. An increase in extreme weather events like heavy rain, strong winds, intense tropical cyclones. The frequency of tropical cyclones may not go up. When tropical cyclones form, it will be very intense. It will quickly intensify into a very severe storm. And so the damages which can come from tropical cyclone will increase in the future. And convective storms like severe thunderstorms, etc. No change in mean monsoon rainfall. That's very good news. So we will still get an adequate amount of rainfall. An increase in variability of monsoon, more floods and droughts can happen. An increase in sea level and also coastal erosion. So these are the very things which we are very sure about, which will happen in 30-40 years. So our policies and should be steered in terms of to take care of this kind of changes which is going to come. And recently a paper has come in Nature. I had not given the reference. It has come out last year. The paper, they identified, the climate scientists have identified climate tipping points. Climate tipping points, these are the points in which there is no point of no return. It cannot come back. If anything goes beyond this, it cannot come back. So it's all tipping points. Have many places it has come out. One is Arctic sea ice. I told it is reduction in area of Arctic sea ice. Atlantic circulation, of course, physical oceanography people will know about the slowdown in Arctic circulation, Atlantic circulation, and especially meridional circulation of Atlantic is very important in terms of climate over US as well as for Europe, and it has also implication over the Indian region. The Atlantic circulation has a slowdown. Amazon rainforest is reduced. Frequent droughts are happening now there, and boreal forest in northern Europe has changed. And Greenland ice sheet is also ice loss is oscillating. And permafrost is thawing in northern parts of Asia. Coral reef in Australia is changing, large scale die off. And in Antarctica, there are two western Antarctic ice sheet is oscillating, loss is oscillating. And also the East Antarctic ice loss also is oscillating. Then Amazon rainforest is frequent also. So these are the tipping points which they identified. So we need to really look at these places very closely and see monitor how these changes are happening. And this is a very interesting slide. World Economic Forum, as all of you know, that is a very leading organization, and they talk about only economics. But recently they came out at 10 top risks for the next 10 years. As a global community, what are the major risks which we are going to face in our next 10 years? And it is not done by our climate scientists, it's done by World Economic Forum. And I thought they will talk about recession in economy or poverty in some places. But they very interestingly, the first five most risks, they are related to environment. First is extreme weather. Second is climate action failure. That means you know that climate is changing, but you don't do any action. For example, US, they are not bothered about climate change. They say that climate change is not happening. That is a climate action failure. Third is natural disaster. Fourth is biodiversity loss. Fifth is human-made environmental disaster. The first five are environmental causes. It's all done by World Economic Forum. The sixth is, of course, data fraud. Seventh is cyber attacks. Eighth is water crisis. Then ninth is global governance failure. And 10th is asset bubble. I don't know what is this asset bubble. But first five I know very well, it's all environment related. So that kind of seriousness is being given by all organizations around the world. So we all should know that climate is changing. It's no more a myth. It is really it's a fact. Climate is changing, and we have seen many examples that climate is changing everywhere. And also, not only some temperature is increasing, it has a lot of repercussion. A lot of extreme weather events are happening, and there are some of the physical processes happening which are non-reversible. It cannot be reversed back. It's all tipping points. We have reached only some 10 places where the tipping points have reached. So very important time now, as we know that COVID is now a present crisis, and along with COVID, we should also read about the impending climate change which is going to come next few years. And so all the governments, all the NGOs, all the research community should really gear up to take up research in climate change, and also related to mitigation effects we should do. And for climate change has a lot of effect in different sectors. For example, climate change can affect agriculture, climate change can affect in water resources, for example, water availability, climate change can affect in energy, for example. And what is the climate change can affect, has an effect in health, for example. For example, many diseases, waterborne diseases, etc., can increase due to climate change. And there are very beautiful examples how the future climate change can lead to many health impacts around the world. And COVID is nothing in that. If you really calculate the adverse health impacts in terms of climate change, the impacts will be much more severe. And this is a beautiful cartoon I made. I used to normally do it everywhere. I show it everywhere. The top one, I'm sure that people are seeing it. The top one shows each continent is increased, the size is increased or decreased in terms of its contribution, percentage contribution. The top one shows that cumulative emissions of greenhouse emissions. You can see North America is shown as a bigger one because it has a larger ratio, larger contribution. Europe also is a larger contribution. India is shown as India, so it's not much change. But when down, if you really see how the impact of mortality from climate change, the things are different. Europe and America will not have any effect on health. The climate effect will be on health will be more on Africa, more on Asia, and poor countries. So somebody else is emitting more of greenhouse gases, but when it comes about health impact, it will be of poor countries like Africa who is not emitting anything of carbon dioxide. So that is the irony of climate change. Climate change is not an equal distribution. It is very uneven distribution. People are emitting, and some people else is having the effect of climate change. So that's a very unfortunate situation. It's happening, but it's a real story. I'm not telling about fake stories. They're all real stories, all done with observations and evidence. And it's evidence-based stories I'm talking. And so that's all I want to say. And it's the last slide. So let us save our beautiful blue planets. May not be for ours, but at least for our children and grandchildren. I think we should preserve our blue planet. We should do well. With this, I will stop. And once again, thank you, Dr. Sunil Singh, for giving me a good opportunity to talk to all of you. Thank you very much.
Thank you very much, sir. Thank you very much for giving this very insightful talk on climate change and covering so many things from defining the climate change to ocean heat content, its impact on cyclones, sea level rise, ocean acidification, impact on Arctic melting, and showing that by 50, Arctic will be free of ice, teleconnection of Arctic and Indian summer monsoon, how the temperature will change, how the cold and cold nights will be disappearing from the northern India, rainfall increase, decrease, so many things you talk about. I think you have clarified so many doubts which we are having. You told about the heavy rainfall, extreme rainfall, how it will increase or decrease. And a good news that monsoon will not change, but the regional changes could be there. Heat wave will be increasing. And impact of aerosol you have talked about, and also the impact of biogeochemistry, deep ocean on the a little bit longer climate change, what impact it will have, and how the MOES is trying to do the Earth system modeling to predict, project the climate projection. And what is the impact on Himalaya? How the temperature is much more changes are happening in Himalaya compared to the rest of the India. Rainfall will increase. I think so many things you talked about. I think it was very enlightening talk. I'm very much thankful to you, sir, to giving such a wonderful talk. And maybe I think we'll have some query. I think I see one raised hand by Satish, Dr. Satish Shanwai. Shanwai, do you want to ask something?
Please unmute your mic and start.
Dr. Satish Shanwai?
Yeah, can you hear me?
Yes, sir, yes.
Can you hear me?
Yes,
okay.
Yes.
This is a question, comment on the last slide. It was a wonderful talk. It was very informative. Thanks to Dr. Rajeevan for a very informative talk. That last slide showed that which are the countries which are increasingly emitting. That seems to be very correct. But the bottom, it showed that the countries where the mortality will increase because of the climate change, the pandemics. But from the COVID experience, it clearly shows that North America or Europe is not as expected safe. And on the contrary, the Africa is more safer than those countries. So I think WHO has to rethink on this projection that others are going to die. No, I think the climate change is going to kill more in Europe and America from the COVID experience. Thank you.
Thank you. Thank you.
Anybody else want to ask something? I think the talk was very clear, sir. I think, and from this talk, we also got to learn so many things, and also we learned that NIO can do many things on many of these topics which you have talked about. So I think it will be very good that our scientists will be working some of these topics. Thank you very much for this insightful talk and sparing your time. And we are really thankful to you for giving this talk and sparing your time. And hopefully sometime when you are coming in next time, physically we'll have this type of wonderful talk from you. Thank you, sir. Thank you very much.
Thank you. Thank you. Thank you very much. Thank you. Thank you. Thank you all of you. Thank you.
And thank you everybody for attending this talk. Thanks a lot. We will conclude here. Thanks.